I want to talk about a practical coordination stack for cloud systems. Let me start with the failure. Two users try to buy the same seat in a theater for a concert at nearly the same time. I'll click into our demo app here, CosmicTix, and I'll browse the seats that I can buy. Now I'm logged in as Alice, and you'll see that I have some options here. I'm going to turn on this race simulator. And I'm going to simulate this race condition that we just talked about, two users trying to buy the same ticket at the same time. So when I do that, you'll see that this ticket, floor right, row 3, seat 7, both Alice and Bob tried to buy this ticket at the same time, and they double booked this. They both think, if I look at my tickets, Alice has this ticket. And if I look at Bob, Bob thinks he also has this ticket. I'm going to switch back to Alice. And we'll come back to her and buy some more tickets in just a minute. That last write silently overwrote the other one. And one user walked away thinking they bought the ticket, but they can't possibly both have those tickets. There's one seat. So this is not a weird edge case. This is what distributed systems do when concurrency is real and coordination is missing. The first problem is the simplest one. Two writers, the same record, the last write wins. Now, if you do nothing, silent data loss is the default behavior. Now, make it worse. Two processes read the same state and both send an email, or both call a payment processor, or both hit some external system that you don't control. At that point, rollback is mostly fiction. Now, make it a workflow. You save something, you call another service, maybe send an email, and step 3 or 4 fails after earlier work already happened. That's the beginning of Saga territory. And then the retry happens. But now the retry can duplicate these side effects. And that is why this talk exists. So the question is not just how to store data. The question is how to coordinate work correctly under concurrency, failure, and retry. Before I get too far ahead of myself, I'm Eric Boyd. I have been in technology and software development for 30 years. I'm a 15-time Azure MVP. I'm also an AI or Microsoft Foundry MVP. And I'm also a Microsoft Regional Director. I run responsiveX. We help customers design, build, and modernize cloud-native applications, data platforms, and AI-driven systems on Azure. That work sits right at the intersection of user experience, distributed systems, DevSecOps, and AI, which is exactly why this topic matters. Now, before I name Cosmos DB specifically, here's what the platform has to give us. We need a way to stop overwriting data we've not seen. We need a way to react to changes. We need a way to expire data automatically. We need throughput scale and storage scale. We need low latency and multi-region capability and failover. That is the selection criteria. Now we can talk about the building blocks. Cosmos gives us the primitives we need. E-tags plus conditional writes give us optimistic concurrency. TTL gives us lease expiration. Change feed gives us durable notification of changes. Partitions give us scalable key distribution. And global replication, routing, and failover, they give us the operational footprint to run this in real systems. Now, everything else in this talk is built on those primitives. I'm going to reproduce that seat purchase race condition, but this time the write that I'm going to do will include that e-tag. So I'll go back to CosmicTix. And here, I'm going to simulate, I'm going to go back to actually buy tickets for Alice. I'm going to go back to that same concert or event. And here's my race condition demo again. You'll see Alice only has this one, or thinks she has this one seat at the moment. I'm going to simulate that race again. And now you'll see in the upper left, we bought a ticket. Alice bought the ticket. She won or got the ticket. Bob, in this race condition, failed. It says it was taken by another buyer. So only one buyer got the seat. Now, previously, Bob had one ticket. If I go look at Bob again, and I look at my tickets for Bob, you'll see Bob still only has one ticket. That ticket up in the upper left-hand corner did not get attributed to Bob. And so that's all using those E tags. So let's go back and talk about what just happened. Now, both users retrieved a document before any updates, and it had an E tag. And we'll say this E tag starts with value V1. Buyer A writes and succeeds. Buyer B writes with a stale E tag. So Cosmos rejected that write instead of just silently accepting it. Now, the race still happened. That part didn't just disappear. What changed is the platform detected that the document had changed after the read, and it refused that stale update. So the E tag doesn't eliminate the concurrency, it just turns that silent corruption into an explicit conflict. The code pattern is pretty straightforward. We'll read the document that contains the seat. We'll capture the resource data. We'll then capture the E tag. We'll modify the document. We'll write it back, but we'll do it with this if match E tag header. Now, if Cosmos returns a precondition failure, we're not going to pretend it was successful. Instead, we'll tell the user the seat changed and they need to refresh the availability. E tag solves one document writes, but it does not solve these longer critical sections. For example, if the operation is read availability, place a hold on a seat, update related state, trigger follow-up work, well, two workers can still overlap in that unit of work. Even with those per write E tag protections, the section level race remains. So you need exclusive access around that full critical section. If we step this up to a distributed lock, maybe we can get that. So let's go back to our race condition and let's try another scenario here. I'm going to go into that same event or concert. And this time I'm going to turn on a different feature. Instead of the race simulator, I'm going to turn on best available. And what best available does for us is this. We want to buy some number of tickets. In this case, we're going to say 2 tickets. We don't want to pick the exact seats. We want the system to choose the seats that are best for us and just purchase them for us. Now, the challenge with this is the system has to go out and see what's available. It then has to get a hold of whatever number of seats that we've asked for and buy those before somebody else does. And so we need to have some way to kind of temporarily hold those so that no one else can buy them while we're sorting out from all the available seats which ones are actually the best. And so I'm going to start by just running this, and I'm going to simulate this race condition. And what we should see again here is 2 people, Alice and Bob. They both got the same seats. They both bought what we think are the best seats in this venue, floor center, 5 and 6. So both of them have them. Well, that can't happen. Again, we can't sell the same seats to 2 different people. So if I change this and I say, let's use a distributed lock here. So behind the scenes, I'm just toggling on a distributed lock feature. And we go try this again. And I say, simulate this race condition. Well, now you'll see that Alice and Bob still successfully bought seats, but they actually bought their own seats. So Alice got seats in that center floor section, row 1, 3, and 4. Bob got seats in that center floor section, row 2, 5, and 6, that dead middle center area. So in this case, that distributed lock worked. It held on to tickets, bought them, let them buy the tickets before letting somebody else get in there. Let's go back and explain really what happened here. Process A acquired the lock for the seat and it entered into that critical section we talked about earlier. Process B tried to acquire the same lock, but it couldn't. It couldn't proceed with that resource, with those specific seats. Only one user was able to get to that sensitive critical section at any given time and do the operation. Now, when the lock is released or it expires, then process B could get a hold of this. In this case, Alice and Bob fighting for the same tickets. In code, it's pretty simple. I'm going to build this in what kind of looks like an awkward way, but the first thing we're going to start with is what we want to do. We want to do this protected work. We want to reserve a seat for an individual buyer. Well, to do that, we need to acquire a lock. We need to enter that critical section using a wait, wrapping that with a using block with a wait. And then we will release it because of that await, that disposable pattern. We're going to release it automatically when that handle is disposed. We'll handle any errors that occur and react appropriately. And if the acquisition fails, we don't let the second worker continue. Now, this is where teams get themselves into a little bit of trouble. The first thing to talk about is fence tokens. Now, if a worker pauses, its lease can expire, and the worker then has a token and it becomes a zombie. What I mean by that is another worker can take over, and then that original worker, if it wakes up, it's a zombie, but it can still resume unless we protect the resources by using some monotonically increasing token. And this is where fence tokens come into play. The second is renewal. Leases expire on wall clock time. So if the worker runs long, the lease, you have to renew it. If the renewal fails, you have to stop. You no longer own that lock exclusively. And then third is retry. Under contention, backoff and jitter are not optional. Uniform retries can create a thundering herd attacking and going after these locks. Now we're going to step into a different class of problems. Locks are great for those short, critical sections. They are the wrong tool for long-running workflows that cross service and network boundaries. In Cosmic Ticks, a purchase flow may reserve inventory. It may charge a payment, send confirmation, update several pieces of state. You can't responsibly hold a short lease around that entire journey. So let's take a look at this in a workflow version of this problem. So I'm going to change my config just a little bit to say we're going to use a different purchase mode. And in this case, we are going to use Sagas to accomplish these purchases. I'm going to go back to our seats in our concert venue. I'm not going to use best available here. Instead, I'm just going to say, let's buy a single ticket. So I'm going to pick this ticket and I'm going to say, let's buy it. And when I do that, it says my purchase succeeded. There's no contention on that. But what actually happened? Well, if we go look, I'm going to turn on my activity log and we're going to see I attempted to make this purchase. I started the purchase saga for one seat. And as part of that workflow, I did several things. I held the seat. I charged the card. The payment was approved. And then I issued tickets with the ticketing system. And then I sent an email or a confirmation notifying Alice that she received and bought these tickets. So that was my saga. Those were my multiple steps in the workflow. But what happens if a failure occurs? What happens if maybe the credit card processing system is failing? So I just turned on a toggle that says, let's fail credit card processing. And we are going to buy another ticket. So I'm going to go down to the lower right section. It's a little cheaper. I'm going to buy these tickets. And what we're seeing now is I started that purchase saga, but the purchase was rolled back. You'll see up here, I don't have that in a red dot anymore. I didn't lock up that ticket. The saga started. I held the seats. I tried to charge the card, but the payment was declined. And so it compensated. It released the held seats and it returned them back so I could buy them again. The credit card payment failed. Well, what if it fails at a later point? What if the card payment goes through, but the ticketing system has a failure? The ticketing system is down or something like that. Well, let's turn that on. So I've turned on the ticketing system failing. We still have that same seat available to us because it failed the last time, Let's try to buy it again. And now in our activity log, we see the purchase was rolled back. But when we tried to buy the ticket, we reserved and held the seat. We charged the credit card. That went fine. But we couldn't issue the ticket because the ticketing system was down. And so here we compensated by refunding the card, releasing the seats, and it's still available. All right, let's talk about what just happened here and how we did it. So a Saga treats this workflow as an explicit state. We have one Saga document per purchase in this case. Each step moves through this state machine, and each step moves it forward conditionally. The document records what completed, what's coming up next, and what must be compensated if a recovery is needed. Now, on retry, resume from the recorded state is what we need to do, and then we need to skip the completed states. On a failure, we want to execute compensation by kind of backing up through it in reverse order for all of those committed steps. Now, from code, we can look at it like this. So I built a little library here, and I'm kind of hiding what's underneath here, but I'm going to share that code with you at the end as well. So if you think about it like this, we need to load or create the Saga instance. And so we have all these steps that we identified: hold seats, charge card, issue tickets, send confirmation. And in each of those, we have, here's the process we're trying to do. Here's what we do if we need to compensate. So we hold seats, we release seats, we charge card, we refund card, we issue tickets, we revoke tickets, on and on. Then we execute the next steps based on the current state. We write the transition with optimistic concurrency and record completion before we move on. On retry, we would resume from the recorded state instead of replaying the work blindly. And when the Saga execution completes, we're going to react to the result. And so here we're going to get that result back, and we're going to do whatever we need to do with that. The purchase was completed, it was rolled back, and we saw those toast notifications in the app. Now, there's some details that matter when we make this work. First, every step must be idempotent or guarded by a recorded completion. Compensation is deliberate. You saw the compensation step: refund card, release seats. Those are deliberate. They're not magic. They're not some sort of magical rollback. And the compensation intent, it should be written ahead of time. So if the process crashes mid-step, recovery still knows what to do to undo or counteract that. ETAG conditional rights protect Saga state transitions against these kind of racing executors that we saw. Now, suppose the workflow succeeds, but you still need to tell other systems. If you save the state and then publish directly, there is a crash gap that occurs between the commit and the notification. You need the intent to notify to be as durable as the state change itself. And so this is where the outbox comes into play. So I'm going to go back to my application, and we'll take this scenario, for example. One of the things you saw in the code was there wasn't a compensation step for messaging. And so if we simulate a messaging failure here, and in this case, we try to buy the tickets, you'll notice the purchase succeeded. We got all the way through the Saga, but at the end, we didn't actually send the emails to let the users know that they purchased the tickets. Now, me as a user, I know I clicked purchase on the tickets. I saw the toast notification come through. I see it in my account in the app. And so the notification is not super important. But what if I'm transferring tickets between two users? So let's go over to the tickets that I already have. And these are my active tickets for this concert. And let's say I want to transfer as Alice one of my tickets to Bob. So we'll pick this one right here. And in this case, I'm going to leave this messaging failure in place, and I'm just going to try to transfer this ticket to Bob. So the tickets say they transferred successfully, but we have a messaging failure. So Bob doesn't know that the ticket was sent to him. He never got a notification of that. And I also wanted to send a notification to Alice just as a receipt as well, that she sent the tickets to Bob, but she didn't get that either. But the ticket did leave Alice's active tickets. Well, what if we change this and we use an outbox instead of just doing it transactionally like we're doing now? And we'll grab another one of these tickets. I'm going to grab this ticket in the upper left-hand corner. And again, I'm going to transfer it to Bob. And I'm going to just press transfer here. Now, in this case, the ticket's transferred successfully, but you'll see we wrote it in the outbox. And so the publish failed. It's not able to send the notification, but it's in the outbox and it knows that it needs to. And it's holding on to that because it happened as one transactional write. And so if the messaging system gets fixed, I'm going to fix it right now. Then what we'll see is because I'm reprocessing and responding to the events in the outbox, eventually we'll see the messages succeed, and we'll see a message go out to Alice and a message go out to Bob, and there they are. The previous owner got a message delivered, and the new owner got a message delivered that they've received the transfer. So you can think of this as two stages. Stage one writes the business state as a pending message together. Stage two is a relay that reads the pending messages and publishes them and marks them sent. The outbox closes the gap between those state changes and the intent to notify. So what you're guaranteeing is at least once delivery, so downstream handlers still have to be idempotent. And in code, you can think of it like this. When the purchase completes or the Saga advances, I'm going to create a transaction. I'm going to write the domain change in that transaction. I'm going to also write the pending outbox record in that same durable operation. I'll save or execute the batch, and then I'll have a worker read the unsent messages. I'll publish them and I'll mark them as dispatched. The outbox is not exactly once. It's at least once. That means retries can duplicate publication, so handlers must be idempotent. You also need operational visibility into relay lag, backlog growth, and recovery after crashes. Here is the production reality check. Consistency level matters. Multi-region writes can violate coordination correctness if two regions both accept conflicting conditional operations before convergence. And hotspots matter. How you partition your data matters. The retry behavior also matters. And once you add outbox, at least once delivery and relay backlog become operational concerns, not these theoretical ones. So for coordination data, correctness is going to beat convenience every time. So the pattern map is simple. Use ETAG for single document concurrency. Use a lock for short, exclusive critical sections. Use a Saga for multi-step workflows. Use an outbox for reliable post-commit publication. Do not use timestamps as ordering truth. Do not hold locks across those external calls. Do not assume direct publish is safe after. If you want more detail, I'd encourage you to visit ericboyd.com, and there you'll find a companion article with the patterns, code, and resources. You'll also find the sample code and the deck links there too. Thanks again.